Hi everyone. In this video we are going to discuss proof of one theorem. So that theorem is, if the matrix space has BWP, then it is sequentially compact. BWP, that means Bolzano-Weierstrass theorem, and definition of sequentially compact matrix space we have already seen in previous videos. So let us recall the definitions first and then we will start the proof. Okay. So the first one is BWP, means Bolzano-Weierstrass property. See, this property says every infinite subset of matrix space X has a limit point. So definition, that property says every infinite subset has limit point. Okay, every infinite subset of a given matrix has a limit point. And the second is sequentially compact matrix space. Sequentially compact matrix space means every sequence has convergent subsequence. Every sequence is convergent subsequence. So in this theorem, this is a given part. They have given the matrix space has BWP. And what we have to prove? We have to prove that it is sequentially compact. That means this thing we have to prove. So let us start with a given information, right? So let me write here. We have a matrix space XD and it has BWP. So it has Bolzano-Weierstrass property, and what we have to prove? We have to prove that it is sequentially compact. So let me mention here, to prove that XD is sequentially compact. So we have to prove that it is sequentially compact. Sequentially compact, that means what we have to prove exactly? We have to prove that every sequence has convergent subsequence. Every sequence. So let us take one sequence Xn and we will prove that it has a convergent subsequence. So let us take one sequence Xn. Let Xn be any subsequence. Sorry, Xn is any sequence in a matrix space XD. It is any sequence in matrix space XD. And what we have to prove? We have to prove that it has convergent subsequence. Now this thing we have to prove. So every sequence, I have taken one representative of every sequence Xn and I have to prove that it has a convergent subsequence, right? So this thing we have to prove. So I am going to consider one range set of sequence Xn. So let A be a range set of, let me remove this part, it is not required now. Okay, so just a minute. A be any range, A be a range set of sequence Xn. So let us talk about what is range set. What is range set? Consider one sequence Xn is equal to -1 raised to n. So what will be the terms of that sequence? So the first term is obviously -1, the second term is 1, third term is -1, fourth term is 1, fifth term is -1, next term is 1, and so on. So in this way we will have terms of that sequence Xn. So we can easily observe that there are only two terms which are repeating infinitely many times. It means the range set of sequence Xn will have only two terms, -1 and 1. And yes, with the help of these two terms, the entire sequence is formed. Get it? Let us discuss one more example. If you have a sequence yn, which is defined as 1 by n. So you know that the terms of sequence 1 by n, which is first term is 1, the second term is 1 by 2, the third term is 1 by 3, the next term is 1 by 4, 1 by 5, and so on. So this is the second example. So let us talk about its range set. I am denoting the range set of this sequence by B. So tell me what will be the terms here. So we can easily observe that there is no any term repeating itself in a sequence. So that's why the range set will be all terms of a sequence 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5 and so on. So same all terms of a sequence we will have here since no term is repeating here. right? So this is a range set. In a first example, we got a range set having only 2 elements, but in a second example, we got a range set having infinitely many elements. So obviously, here also we need to discuss two cases. The first case is range set is finite, and the second case is range set is infinite. So let us go with a first case, that is range set is finite. So let me mention here case number 1, that is A is finite. A is finite. See, the range set is finite, having only finite number of elements. So let me remove the second example. It is not required now, since we are discussing a first case where the range set is finite. Okay. So here the range set is finite. So with the help of finite number of elements, we have to form an entire sequence. That means at least one term should repeat infinitely many times. You are getting my point? Let us discuss one more example so you can easily understand. Suppose I am giving you the range set B is equal to. So we have a range set 1, 2, 3. Only 3 elements, since we are discussing a first case where the range set is finite. So here I am considering a range set is finite. You can denote A, B, doesn't matter. I am denoting it by A again. So now we have to form a sequence Xn having a range set A. Getting? So with the help of 1, 2 and 3 only, we have to form an entire sequence. You know that in sequence there are infinitely many elements, right? But we have just finite elements to write. So the sequence can be 1, 2, you can take 3. Getting? So we want to write next number. So you can take from these numbers only. So you can take 2 here, right? Next term will be, you can take 1, 2, 3. So I will take 3 here. The next term will be, again I will take 3, 3. Again I will take 1 here. Getting? So now 3, 3 and so on. So with the help of finite elements, we are forming a sequence. It means at least one element appears infinitely many times. Okay. So A is finite. So then at least one number appears infinitely many times in a sequence. Getting? So range set is finite. That means at least one number is appearing infinitely many times. You can see here the 3 is appearing infinitely many times. Okay, in this example I have taken. So let us go further. Now what will I do? I will consider a subsequence. I am going to construct a subsequence of sequence Xn of that number only, which appears infinitely many times. Getting? So let me mention here. Consider a subsequence Xnk of that number or that term only. Okay, that number or that term only. So that means in this example, so you know that this is sequence in which 3 is appearing infinitely many times. So let me call it as Xn1. Let me call it as Xn2. This is Xn3. This is Xn4. This one is Xn5. That means I am choosing only 3 and I am forming a new sequence, okay, from those elements. So obviously it is a subsequence of Xn. So the Xn1, that means that Xnk subsequence will look like this: 3, 3, 3, 3, 3, since I am choosing this 3 only. So the same thing I am doing here, at least one number or at least one term appearing infinitely many times, it means we can consider a subsequence Xnk of that term only. Getting? So obviously it's a constant sequence. So let me mention here, therefore Xnk is a constant sequence. It's a constant sequence. Getting? And we know that every constant sequence is convergent. Therefore Xnk is convergent since it is a constant sequence. Getting? So it's a convergence. So what I want to say, we started with one sequence Xn and finally we got its convergent subsequence. So let me mention here, let me remove this example. It is not required now. Okay, just a minute. Therefore sequence Xn has convergent subsequence xnk, has convergent subsequence xnk. So we started with one sequence and finally we got it has a convergent subsequence. This is definition of sequentially compact metric space. So every sequence has convergent subsequence, therefore we can declare X is sequentially compact. Wait. But this is, we have proved only for first case. We have to prove the same thing for the second case. So let us go for the second case, right? So in this case, we proved Xn has a convergent subsequence Xnk. So let us talk about case number 2. So the case 1 is A is finite. So obviously the second case will be A is infinite. Case 2 is A is infinite. That means A has infinitely many elements, right? But do you remember we started with one given information and still we haven't used it. So what is the given information? The given information is metric space has BWP. Okay, so this is a given information. So let me mention here X has BWP. So let us recall what is that BWP, Bolzano-Weierstrass property. That property says every infinite set has a limit point. Do you have infinite set? Yes, right now we have it. So A is infinite set. So the Bolzano-Weierstrass property says that infinite set has a limit point. So let me mention here X is BWP, therefore A has limit point. Why we can say it has a limit point? Because it is an infinite set. X has BWP, therefore every infinite set has a limit point, therefore A has also limit points. So let us call it as X. Say X. So do you remember the definition of limit point? Okay, so the definition is, therefore the definition of limit point I am simply writing BXR minus singleton X intersection A not equal to phi, and this is true for every r greater than 0. So I simply use the definition of limit point. Getting limit point of definition of limit point says BXR minus singleton X intersection A not equal to phi, and this is true for every r greater than 0. See, there is no more space to write. Make a screenshot of it, then I will go further. So the most important thing is this is true for every r greater than 0. That means we can take r is equal to 1, then this is true, r is equal to 2, 3, 4, r is equal to 100, 1000, doesn't matter. This is true for every r greater than 0. So in particular, I will take r is equal to 1. Let us see what will happen. So for r is equal to 1. So tell me what can we write if I put r is equal to 1. Okay, this will be true for r is equal to 1 also. So bx1 minus singleton x, right, intersection A not equal to phi. Simply at a place of r, I put 1, right? So I got this one. So in a diagram, see what will happen actually. So this is set A we have, getting this is set A we have. We have a point x somewhere here. So we are considering a ball with center x and radius 1. So yes, so I am taking a radius 1 and I am drawing a ball around it. So this is radius 1 and this is the center of that ball, getting? So bx1, that means this ball, minus singleton x. So we are removing the center, intersection A, this is set A. Intersection, you can easily see this is the part, this part is in intersection. So which is non-empty. In diagram also you can easily see that intersection is non-empty. So intersection is non-empty, that means at least one point will be there. So let me call it as xn1. Okay, so therefore I can choose one point. xn1 belongs to bx1 minus singleton x intersection A, right? So let me tell you why I am calling it as xn1 instead of saying x1. Basically A means what? Do you remember? A is a range set of a sequence xn. We started with a sequence first, then I took range set and that is A. So basically there are terms of sequence only. So xn, x1, x2, x3 and so on. So I am taking one point, so that's why I should call it as xn1 since it is a term of a sequence. That's why, right? Let us go further. So r is equal to 1, r is equal to 1 I put, I got this one. So let us put r is equal to 1 by 2. Let us see what will happen. For r is equal to 1 by 2, what will I get? Simply I am putting r is equal to 1 by 2, bx half minus singleton x intersection a not equal to 5. So now what I am doing, simply I reduce the radius. So now the radius is half. So let me show here, we got one point x and 1. I have taken one point from the intersection, so I took one point. So now I reduce the radius and now the radius is half only, half of the previous, getting? So again the intersection is non-empty, that means we can choose one more point. So let me call it as xn2. I am calling it as xn2. So I can choose one point. Okay, so therefore we can choose xn2 belongs to bx1, sorry, bx half I should write, minus singleton x intersection a. See, the same thing we can repeat for r is equal to 1 by 3, getting? So if you reduce the radius, it will be 1 by 3. This time you can choose one point xn3. Again I can reduce the radius 1 by 4, xn4. So you can repeat this procedure infinitely many times. So let me write in general what can we write? Bx 1 by k minus singleton x. Okay, so k is any natural number, 1 2 3 4, intersection a not equal to 5. So in general for any k, okay, 1 by k, so you will have this set non-empty. So again we can choose one point xn k. Let me write this one, just make a screenshot of it. Okay, see, so therefore we can choose one point xn k. So let me mention, we can choose one point xn k belongs to bx 1 by k minus singleton x intersection a. You are getting the point? So all these are concentric circles. First we took a circle with radius 1, next half, next 1 by 3, 1 by 4, 1 by 5 and so on. And from each circle we are selecting one point, xn1, xn2, xn3. Let me show some points here, xn2, xn3, xn4 and so on. So you can easily see that sequence converges to x. All these points are moving towards a x, since each time we are reducing the radius of a circle, right? So let me extend it and so on and so on. So basically xn k belongs to bx 1 by k minus singleton x. It lies in intersection, that means it lies in first set as well as it is in second set. So I am considering it is in first set. Therefore xn k bx 1 by k, getting? For all k belongs to set of natural number, getting the point? See, bx 1 by k, actually if you remove x, then also all these points lies inside a ball. So I can easily see it lies inside a ball. Okay, so make a screenshot of it, then I will go further. So let me show you what is actually happening here. Okay, what is actually happening? So we have a x, we have a ball here having radius 1 by k. So this radius is 1 by k, right? And xn k, one point we have xn k here inside a ball. So you know that if any point lies inside a ball, the distance of point from the center of ball is less than its radius. So I can write here. So therefore distance between xn k and x is less than radius, which is 1 by k, getting? But we know that as k tends to infinity, 1 by k tends to 0, as k tends to infinity, getting? 1 by k tends to 0, that means distance between xn k and x, that is also tends to 0. This is the distance, you know, it cannot be negative. We are saying it is less than some number which is converging to 0, that means this distance also converging to 0 as k tends to infinity. Distance between two points, you can say these two panes I have, This they have the fixed distance between them. So that distance is moving towards 0. That means both planes are moving to each other. Getting? Distance is 0, or either you can say the one plane is moving towards the second plane if the second plane is fixed. Here the point x is fixed, x and k can move as n varies or k varies. So x and k converges to x. So therefore I can say the sequence x and k converges to x. But basically it is a subsequence of xn. So therefore I can say, therefore xn has convergent subsequence xnk. xnk, getting? So xnk is a subsequence of xn which is convergent. In second case also we proved xn has a convergent subsequence. You know that in first case already we have proved every sequence xn has a convergent subsequence. That means in both cases we got a convergent subsequence for sequence xn. So therefore from both cases we get a sequence xn has convergent subsequence. Sequence xn has convergent subsequence. Let me remove this part, okay? Just a minute. Yes. So we took one arbitrary sequence xn, and in both cases we proved it has a convergent subsequence. So let me mention, therefore every sequence in X has convergent subsequence, and this is definition of sequentially compact matrix space. So therefore I can declare, therefore X is sequentially compact. Getting? X is sequentially compact. So in this way we proved if the matrix space has BWP, it is sequentially compact. Okay. So proof is over. Make a screenshot of it, then we will stop. Thank you. See you next time.